We're doing part B on 12.1, 12.2, and 12.3, reflections, translations, and rotations. It'll just be more of an expansion of what you've already heard with regard to the functions. So we know what they can basically do, and we'll expand on that, and we'll define some terms as well. So you might see some words that we haven't really used in class yet. We'll use those. And also, we'll be doing things with what are called matrices. It's something you'll do a lot in Algebra 2 Trig, and we'll give you a basic idea of it with matrix addition, and we'll use it for translations. Okay, a couple definitions to start off. Pre-image, image, and isometry. A pre-image is it's the image that you have before you make a transformation on something. So let's say that I have a triangle. And it's called ABC. Okay, that's my pre-image. It's the image before my transformation. The figure after a transformation is called the image. So let's say that I reflected ABC across this axis of symmetry right there. An axis of symmetry I actually don't have on the notes, but that's another term that you will have to know. It's the axis for which you draw your reflection. You draw a mirror image. So here's my pre-image, triangle ABC. Here's its reflection, A prime, B prime, C prime, and that is called the image. So if I say something about from pre-image to image, or connect the pre-image and the image, this is what I'm talking about. And finally, in isometry, it is when both of these are congruent. In other words, AB, the length of AB, is congruent to the length of BA. Angle C, B prime, A prime. Angle C is congruent to angle C prime, etc. So all of these things have to be congruent after the transformation. Your pre-image and your image are the exact same. And you've probably noticed that when you're doing a rotation, a reflection, or a translation, they do appear to be the same. There's a time when they won't be, and that's called with a dilation. And that basically makes the images similar, but not congruent. Okay, we're going to do reflections with the pre-image on the axis of symmetry. So we've seen a lot of things where we reflect it across something. Let's say we reflect this one across over the x-axis here. So we've done them in class where, let's say we had our shape here and we reflected it across, so it looked like that. And we're like, okay, that's easy because you just calculate how far away it is from the x-axis. But this time it's actually on it. So how do we flip it? Well, the idea here is that you still want to flip the individual vertices and then draw the image. So go 1 point at a time. Let's take A, and let's see how far away it is from our axis of symmetry. In this case, it's on the axis of symmetry. So what's going to happen is a point on the axis of symmetry remains unchanged after a reflection. So A prime is in the exact same place. You might see me, or the book sometimes write A equals, that should be an equals. A equals A prime. They're right in the same place. B, on the other hand, you count it. You go 1, 2 units away from the axis of symmetry, and flip again, 1, 2. There's B prime. And C prime, 1, 2, 3, 4 units away, 1, 2, 3, 4 on this side. So there's C prime. And together we would connect a triangle that is flipped like so. So there's your flipped mirror image. Even though it can't all look in the mirror at the same time, if that makes sense, you can't look at the object as a whole. You have to look at individual points and then flip them. So let's do another problem, and let's reflect it over x equals 4. So my axis of symmetry here, x equals 4, you have to know, first of all, what x equals 4 looks like, and then you have to draw it. So let me go and do that. So x equals 4 is every point for which x equals 4. So for instance, when y equals 0, x equals 4, y equals 1, x equals 4, etc. So this is my line, x equals 4. That's my axis of symmetry. And I want to reflect all the points around it. Hopefully you can do this on your paper, and I'll do it right here. 1, 2, 1, 2. There's A prime, 1, 1. C prime, and B prime is on the axis of symmetry, so B prime will be right there as well. And we connect them again. and we get our reflected image. Okay? Okay, reflection on a skewed axis of symmetry. Skewed basically meaning not horizontal, not vertical. I'll call it diagonal, if that makes sense. This will be a little tricky. Not so much by the definition. The definition, the steps are a little tough too, but you have to really know how to calculate the distance and stuff. Okay, find the opposite reciprocal. Now you've heard that word before. That means, well, find the opposite reciprocal of the axis of symmetry. Basically meaning find the slope that would be perpendicular to the slope of your axis of symmetry. So let's say that I had a skewed axis of symmetry right here, and it's some slope. Let's call that slope m. I have to find the opposite reciprocal, the one that would be perpendicular to it. So let's say it's probably about that line right there. I wouldn't just draw it, though. I'd actually have to find it. And if your slope is m, your opposite reciprocal, opposite meaning negative, reciprocal meaning flipping this right here. So m is really m over 1, and opposite reciprocal is 1 over m. Negative 1 over m. So you could use y equals mx plus b form to find that. And then you also find the y-intercept. Also use the same thing. Y-intercept's right here. You have to plug in a point that you know, probably the point that you're flipping. Have that slope, plug in that xy value, and solve for b. And then you have the slope of that line. So that'll help you. And if worse comes to worse and you don't need that, what you can actually do is just find the distance between the point in the pre-image. So remember what pre-image meant there. And the axis of symmetry. The point in the image is the same distance away on the other side of the axis of symmetry. So if you keep in mind, like right here, here's my point, here's my axis of symmetry, here's my reflection. So these are both 2 units away. We know that because we could count right here. But what if I had a point, well, I'll give an example in a second, but basically what if I had a point that was away from it, but diagonally away from the axis of symmetry? So we can use right triangles during the reflection, and I'll show you what I mean in an example, because distance is tough to gauge with diagonal things, and normally we're going to plot our points through, we're going to plot actual coordinate points, so it's probably easier to use a right triangle and just count down and over. Count up, down, and left, right, not diagonally. So I'll give an example of what all this means here. Let's say I have a point R, and I want to reflect it across this dotted line. The first thing that's going to be very important is figuring out the equation of this dotted line. And not just the equation, but definitely the slope. Hopefully you know, in algebra, this is y equals 2x plus 1. My slope is 2, and my y-intercept is 1. Okay, so I have to find the opposite reciprocal of this line. So the opposite reciprocal, as far as the slope is concerned, the opposite would be negative. How should I call this? Let's call this O. This is negative 1/2. The opposite of 2 is negative 2. The reciprocal of 2 is 1 over 2, so the opposite reciprocal is negative 1/2. Now we want to find it where it passes through this point. So if I have a slope that's negative 1/2, and this is drawn to scale, so I can actually just do it right here. But if I have this right here, I want to go, now remember what negative 1/2 x would look like. I go down 1 over 2, down 1 over 2, etc. Down 1 over 2, and keep going. So it should look like that. So if you draw it perfectly and they have tick marks, and you can actually land on the exact point that it crosses through. And that exact point is 1, 3. The mathematical way to do it is I have this equation here, y equals 2x plus 1, and I can plug in this x and y right here into another equation using negative 1/2 as my slope, and I'll find the y-intercept of this equation. And then I can plug these equal to each other and solve for them. So for instance, I'd say 5 equals negative 1/2 times negative 3 plus b. 5 equals 3/2 plus b. Subtract 3/2 from both sides and you get 5 is 10/2. Whoops, what's going on? 5 is 10/2. So 10 halves minus 3 halves is 7 halves. So B is 7 over 2.